Welcome to this video where we'll start section 6.6 on the properties of determinants. The goal of this section is to study the properties of determinants and to apply them to solve problems. Subsection 6.6.1, Determinants and Invertibility. Theorem 6.6.1. Let A be a square matrix, then A is invertible if and only if determinant of A is not equal to 0. So we remember if and only if means that these two statements are equivalent. If you have one, you have the other, and vice versa, and if you do not have one, you do not have the other. So example 6.6.1. For what value or values of x is A singular if A is this matrix here? So we have to remember what singular means, and that is non-invertible. So non-invertible, which means we do not have invertibility. And since this is an if and only if statement, that means we are looking for values of x where we do not have the determinant not 0. Double negative. That means we want the determinant to be 0. So A is singular. A is singular if and only if the determinant of A is equal to 0. Which means that we need to calculate the determinant of this 3 by 3. So we'll do our basket weaving methods. So minus 2, 1, x, and 2, minus 1, 2. We copy the first two columns, x, 0, 3, minus 2, 1, x. And so we are getting here 2x plus 6 plus 0 minus 6 minus x squared plus 0 up this product here, which means that we have this expression. So the 6's are going to cancel out. The negative negatives will give me positive x squared plus 2x, and we need that to be 0. So that is going to be exactly when x is equal to 0 or x is equal to minus 2. So for what values of x, A is singular if x is 0 or x is minus 2. Example 6.6.2, for what value or values of k does this matrix have rank 2? Well, hang on a second, we're talking about invertibility. How come there's a question about rank? So we have to remember that there is a link between them. So first of all, let's give this matrix a name. Let's call this matrix A, and we'll see that our A is a 2 by 2. So when we're talking about an n by n matrix, they're talking about n is equal to 2. And that is a statement of the invertibility theorem that links n by n matrices and their rank with invertibility. So we have that our matrix A, or the rank of A is going to be n, which is 2, if and only if A is invertible. And that is part of the invertibility theorem from a previous chapter, right? That's the invertibility theorem that gives us that statement. Well, theorem 6.6.1 links invertibility with the determinant. So this matrix A is invertible if and only if its determinant is not 0. That's theorem 6.6.1. And so if the rank is 2 if and only if A is invertible, and if A is invertible if and only if the determinant is non-zero, then the rank is 2 if and only if the determinant is non-zero. So we have the following. We've got rank of A equals 2 if and only if the determinant of A is not 0. So that's if and only if the determinant of this 3k1 minus 5 is not 0. And we can calculate that very easily with our 2 by 2 method of crossing our heart. And so we're getting minus 15 minus k, we want that to be non-zero, which means that we want k to be not to be minus 15, and so rank of A is equal to 2 for all values of k other than minus 15. So we can write that as k within the reals without minus 15. So what we have just seen here is a link between one statement of the invertibility theorem and the determinant. Well, if there's a link between one, then there's a link between them all. And that is what theorem 6.6.2 is. It's the fundamental theorem of invertible matrices, or the invertibility theorem, again, the invertibility theorem, version 2. And that is one extra statement, and so we have the same statements as before with the extra statement about the determinant. So if A is an n by n matrix, then the following statements are equivalent, i.e. for a given matrix they are either all true or all false. A is invertible. The linear system AX equals B has exactly one solution for any B. The homogeneous linear system AX equals 0 has only the trivial solution. The rank of A is n. The RREF of A is the identity matrix. In other words, A is row equivalent to I. And here is our new statement: the determinant of A is not equal to 0. In the next video, we're going to see some algebraic properties of the determinant and work on problems using those properties.